everybody, and this is the part 2 of evaluating function arguments in C++. Particularly, we're talking about the evaluation order of functions, or function arguments, rather. So, as always, in this video, we'll be focusing on compiler level optimization rather than algorithmic level optimization, as we are trying to rely on the compiler to generate the best code for us and thus understand the compiler in the best possible way and the most efficient possible way. So, at the highest level as well, or shall we say at the lowest level, because we are looking at the assembly output in order to make the best optimization. So in the previous video we have covered that the evaluation order of function arguments is undefined, it's unspecified. And thus, all of the C and C++ developers, they don't prioritize or they don't write code that relies on the evaluation order of their functions or function arguments. So they don't ever write code that depends really on evaluation order of function arguments. If you want to depend on evaluation order, they usually prefer to write logical operators or implement logical operators and stuff like that that depend on short circuit evaluation, so that we are 100% sure that it's definitely left to right. Whereas with this, it is not only is it not right, left to right or right to left, it is unspecified, since the compiler is trying to generate the most efficient code and the best assembly. So what is an example of why the compiler does this? If we look at the function, if we look at this function, in order to be run, it has to first evaluate. Let's just think of this as left to right evaluation first. So first we try to call the plus, right? But before that we evaluate the left argument and now the right argument. And what if our right argument is function call? You can also look at this as a recursive call almost, but it's written so that it doesn't have a base call or anything like that. It's not typical recursion, but this is what a typical recursion would behave, in that first we need to push the call onto the stack, evaluate the argument, then push another and another and then another, and then at the end we pop the first one, the next one, the third one, etc., up to the point where we are satisfied and we clear out all of the function calls. So in this particular case, the compiler, as it behaves at least recursively, is trying to find the best way to evaluate the function arguments in this case. First one, it tries to read this one and then another one, call, and another, and at one point it will come to this call. And we can see that it's this one that's first called and then this one, and it can be confusing. Why am I first evaluating 7? Am I supposed to evaluate 1 and then 2 and then 3. Well, no. That's because the compiler flips it, right? This is the first argument, this is the second argument. And now I'm looking at the second argument of the second argument and saying, okay, it's more appropriate for me, or for me to be able to generate better code. I want to be able to read or try to evaluate the right argument. And then the right argument in our case at the end becomes this one. And then we look at 6, 5, 4, 3, 2, because they are now left, and it will build up a tree like that. And as we can see in our output, we first have 7, 6, 5, 4, 3, 2, 1. If we use Clang, for example, and I always make sure to show this because this is really compiler dependent stuff or compiler specific stuff. So if I use Clang, I will get 1, 2, 3, 4, 5, 6, 7 as I'm generating it from left to right. And Clang decided to generate it from left to right, or optimize the code from left to right by rather evaluating function arguments from left to right, is that we just got lucky. Okay, so that's not going to be the case always, even for Clang. So that would be that story. So let me go back to GCC and talk about what if we actually want to evaluate from left to right. That's what I talk about one of the previous videos. I mean, the previous video of the series evaluating evaluation order of function arguments in C++. And in that video, I create a macro wrapper for my function that looks like this. Why am I creating a macro? There are some approaches online that advise you or recommend to create a function that would be like this, that has initializer list, and then you are 100%. It is guaranteed that you will now evaluate your arguments from left to right, as initializer list works that way behind the scenes. But the problem with this is, what if my function is something like this? Int character, const character. What now? There's nothing much I can do. So that's why I'm wrapping this into macro. And I'm pretty confident with my macro in this case, as we are there. If you haven't checked out the video C++ statement expressions, do so. And in that video, I talk about how obscure statement expressions are in C++. In that C++ creates a temporary copy in this statement expression scope, and we're literally just creating double copies for no particular reason. But we should be fine in this case if our function returns an x value, like this, inline value. So if we are not returning a const ref or ref or r value and returning an x value like this, we will be fine. There will be no contemporary copies whatsoever. Anyway, to get back to the point, let's actually put this macro to use and see our output. Now we can see 1, 2, 3, 4, 5, 6, 7. Now that's something we wanted to see. However, if we reveal the assembly code, we can see that we are storing a lot of our functions or results or our results to be used as function arguments. We have to store them first somewhere on our stack or somewhere like this in order to use them. And then we can call this tree of functions in order by evaluating them from left to right, left to right. So the problem with this code is, as I've said, is we have too many inner calls in this case. Even though they are immediately it's like call and then pop it and then call it again. We're still sort of exerting our registers by putting too many variables in them or trying to move too much data into them, and because we are trying to make a call to the function. And once we make a call to the function, now we are suffering that push and pop, push and pop. It's not recursive in this case, which compiler does a great job of, but still it's function calls that we cannot possibly inline, as our function is pretty huge. And I did so on purpose so that I can showcase how we can avoid this. How do we avoid too much stuff being moved or too much data being moved onto our registers? Personally, I would just use attribute always inline, and that will do the job for me. Do all the work. And now once I have that, I can see that at no point do I actually make a call to my function. So if we now try to find our code, if one second. Yeah, this code is now pretty difficult to... Yeah, this is going to be a function call actually, because now it's all inline and it's going to be there. Now if we score to source, we should pop up in the function, or not. It cannot find it really. Maybe I'm looking at the wrong piece of code. Let me see. So here, reveal linked code. Now I'm just a little bit paranoid. Is my what is my compiler doing here? Where is my... Let's use O2. It seems like O3 is not really compliant here, and I don't have much time to look at it. And typically you wouldn't need to include, by the way, F jump tables where you force jump tables at O1, O2, O3 levels of optimizations. So this is merely just one of my practices to remind myself of all the compiler options, or at least as many of them as possible. So now this is better, right? Now we are not making a call to the function, to the plus function, and we have generated better code without making any algorithmic improvements. And this is a use case that I have faced in the implementation of my decal programming language, which translates or transpiles into C++. And I've ran into so many hurdles and like evaluating or evaluation order of function arguments. I didn't discover that up to the point where I was making a video, and then I was like, okay, that actually can happen. And because decal executes or applies its binary operations from left to right order of or operation precedence matters in a dynamic language. For example, Python will always evaluate your function arguments from left to right. Make no mistake about it. And at by the way, at O3 level, we finally found our code. You just gotta keep search. You just gotta keep look for it, and you will find it eventually. Alright, so that'll be it for this video. I hope you enjoyed it, and till next time, take care.